content. Let's jump in. Let's not wait around too long. Advent of code day 7. And let's start by reading the problem, okay? We're going to be doing this in Haskell. It's going to be fantastic. So, we've been eating... Giant whale is trying to eat us. Panic. A swarm of crabs. Crabs in submarines. Crab marines. Obviously, crabs are not, really deep sea creatures. They zoom into the rescue. They're preparing to blast a hole in the ocean floor. Sensors indicate a massive underground cave system just beyond where they're aiming. The crab submarines all need to be aligned before they'll have enough power to blast a large enough hole for our submarine to get through. Blah, blah, blah. Crab submarines only move horizontally, of course. So we get a list of horizontal positions of each crab. Crab submarines have limited fuel, so you need to find a way to make all of their horizontal positions match while requiring them to spend as little fuel as possible. So for example, this would be a list of positions, right? So let's draw it. Let's draw it. So let's say we have, hold on. We're working in one dimension here, okay? So our crabs are like here, and here, and here, and here. So if we look at what some of these numbers are, right? So 16 is all the way over here, right? And then you might have like 0 and 5. And we need to find the point, right? Some magical point X where all of the crabs align. And then we need to work out the distance from each crab's starting point to here for how much fuel they need to spend, right? I think I just jumped ahead a bit. But yeah, so each one step costs 1 fuel, and we can pick any horizontal position. So if they align at position 2 here for this example, it has a total costs 37 fuel, it's the cheapest possible outcome, blah, blah, blah. We need to work out the fuel spend, right? The total fuel, so the sum of all of these costs for the position that requires, like, minimizing fuel. Okay. So Haskell gives us a few cool tools to do this. Tools, I almost turned into a Kiwi. We're going to quickly grab a problem input. We're going to make a folder. How about that? Day 7. Okay, let's grab our input. Perfect. So, first things first, we need to model a crab. Crab. Okay, so a crab is just represented by one data point, right? A crab is uniquely, or not uniquely identified, but a crab is, the only piece of data we care about is this single number for its position, okay? Now we're going to do a few different things with these crabs, okay? So, let's take, let's have like a test input, right? And this is going to be a list of crabs. And it's gonna be this, so we're gonna do like an example parse here, I guess. So ultimately, we need to turn this into a list of crabs. Bit of a Haskell quirk here, I guess, right? We have a type called crab. We also have a type constructor called crab. This is going to be confusing, but just bear with me. Perfect. This is going to turn into a list of crabs. Don't worry. It's fine. I promise. Let's jump over Advent of Code 07. And we can load this up in GHCI. We need to give a show instance driving EQ show. I don't need equality, but it's good to pull in equality just for old time's sake. Cool, so we've got a list of crabs. So there are two things we need, right? First, we need to be able to calculate, well, I guess there are two ways to think about it, right? So we want to minimize spend. So we want the minimum fuel spend when all crabs are at the same position, right? So when let's say crab I equals crab j for all I and j, right? For every pair of crabs is at the same position. So we could try and be really smart about this, right? We could have our list of crabs. We could try and like if this crab goes over by 1, if this crab goes over by 1, we could try and minimize by kind of stepping through the entire state, right? And Haskell actually gives you a lot of tools for working with a state like this. So where you kind of have some like initial state, and then you have all of these possible successes, and then they have possible successes. But because of Haskell's laziness, you can kind of have this infinite tree of states and then walk through it to find the minimal case. We're not going to do that. Because if you notice in the solution, right, the position we're going to end up with is actually very simple. It's the position, the only possible solutions, right, in terms of position, are positions where, every coordinate is the same, right? So 0, 0, 0, 0, 0, etc., 1, 1, 1, 1, etc., 2, 2, 2, 2, etc. So it's probably easier to just iterate over all of the possible solutions, calculate the corresponding fuel value, and then take the minimum from that. I suspect, and again, so like we can look at our input, right? What range of numbers are we going to be in? So there's quite a few crabs, right? And they seem to range from, 0 to like, here's a 2,000. And there's what? I can't eyeball how many crabs this is. Let's say this is 1,000 crabs, right? 1,000 by 1,000. We can do that, right? We can brute force that. That's not that big of a number, all things considered, and especially given how simple the calculation will actually be. So there's two things we need, right? So we need a function that's going to say fuel2. That's going to take a list of crabs. It's going to take a position, and it's going to give us a cost in terms of fuel. Fuel2 equals error undefined. And then we also need, well, that's it, right? We just need to calculate the fuel to a point. We do this for every point, and then we take whichever one is smallest. We don't even need to know the coordinate of that position, right? We just need the fuel cost. Okay, so that's easy. That's easy, right? I guess the other question is, what order should these arguments come in? Do we want to take them in this order? Do we want to take them in? It's a small thing. It's a small thing. So fuel 2, we have a list of crabs, okay, and we have a number. Let's do this recursively, right? We have a crab, and then we have crabs. We have some number equals, right? So this is going to be, we're working out this distance, working out this horizontal distance. So all we need to do, let's say we have crab 0, and we're going to position 6. Let's say this is 6, right? So we want the absolute value of n minus the actual integer part. So this is crab I. Right? So this is this, and then we just do it recursively, right? We just add on the cost of the rest of the crab list plus fuel to CSN. I actually don't need that bracket, I don't think. Let's do it anyway, just to be safe. But then we also need the base case, right? Fuel to empty list whatever equals 0. So this is going to calculate the fuel recursively. This one I think is actually really simple. I think we can smash this first part out of the park really, really quickly. So let's say fuel to test 2. And this is the example they give, and the total cost of the fuel is 37. Perfect. This gives a few other examples. So if we go to position 1, we should have 41 fuel spent. Yep. And if we go to position 3, we should have 39 fuel spent. 3, we should have 39 fuel spent. Perfect. Cool. So now we just need to find the minimum fuel, and well, so this is a little bit, I guess, of the tricky part, right? We could just, we need to end somewhere. We could say try position 0, try position 1, try position 2, etc. up to n, but we need to know what the biggest n is. And a pretty sane way to approach that, I think, would be to take whatever the highest crab position is, right? It's not going to be bigger than that. Is it? Ooh. No, it can't be, right? If you have a crab at position 0 and you have a crab at position 1,000, there is no answer that is going to be at position 1,000 and what? Maybe, oh, hold on. hold on. What if... Okay, I'm imagining something here. That's actually a dud assumption, I think, because what if your crabs look like this, right? What if your crabs are here, 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 and here, and here? No, the smallest, like, you're still gonna have this kind of like weighted. It's gonna be between here and here, right? Like, you can't have something out here. That doesn't make sense. That's always going to have a bigger fuel spend than here. Surely the maximum crab is the biggest n we have to consider. That's not a rigorous proof, but I'll take it as a rigorous proof, okay? I'm going to assume biggest crab position is biggest n. So let's get max crab equals, okay, so our max crab, we want to, well, this is actually really simple. We just need to do the inverse of this, right? So here we go from a list of ints to a list of crabs. We want to go from a list of crabs to a list of ints. We can do that by f mapping, well, let's say crab I goes to I mapped over, or actually just f map this. But then we also take the max of this, right? So if I load this in, this should be a function that takes in a list of crabs and gives us an integer. And that doesn't work. Max crab. List of crab to int. I think I've got to actually be properly points free here, right? And then it'll be happy. Nope. Max of, I think I need to maybe bracket this. Cannot match type list of int to list of int with int. So this gives us a list of int max. What is the type of max? Max. Oh, yep. We need to fold this value, right? We need to fold the max 0 over this. Does that work? Yeah, that does work. Okay, so max crab test. This gives us the biggest crab in this list. Cool. So this, I like points free style. I think it's a cool way to write functions. I think it's a good way to interact with Haskell, right? So what we're saying is this part converts a list of crabs into a list of numbers where those numbers are the positions of the crabs, and then this part just, I think there is actually a function that does this over a traversable or whatever, but this is just our way of saying take the maximum value from this list, right? Starting at 0. Maybe let's say like, let's start at 0. That's fine. I don't think there are any negative numbers here, right? I don't see any. We're eyeballing it. The inputs for advent of code are very, very well behaved. Okay, so we can get the biggest crab. Now all we need is to calculate every possible fuel from 0 to max crab, and then we just take the max, right? That's our answer. So fuel candidates. This is going to take a list of crab. It's going to take an int for like the biggest possible number, and it's going to give us back a list of integers, right? The candidate. Or maybe let's just call it solve. Let's just call it solve, and let's just get an answer back at the end. So solve crabs n equals what we want fuel to, we want the folder min. So now instead of doing the max, we do the min of. Actually, no, hold on. We don't need to fold this. So we've got this function solve, right? We have our list of crabs as input, and we have some n, which is like a maximum thing to consider. So we're going to go from 0 to n. At each value in here, we're going to, let's say we have some like I, which is kind of like iterating over this. We're going to call fuel to CSI. So we can do this. I mean, we can just make a list like this. we can just fmap over this list, right? We can fmap lambda I goes to fuel to cs I. So rather than doing anything crazy, right, we can generate a list from, say, 0 to 5, inclusive. Yeah, that's good, that's good. And we can just run this fuel2 function for each value and get the list structure kind of like for free, preserve this list structure we already have, right? Free, I guess, is a bad word there, but this works. And then we just need to folder min 0 of this. So we just take the minimum value from this output, right? So if I say solve test max crab test, we get 0. That's not the right answer. that is not the right answer. Max crab test is 16. Solve test 0 is 0. Solve test, because everything is smaller than 0. So everything is bigger than 0 rather, where this has to be your unit, right? So what we really want here is a number that's bigger than everything else. Is there a general way to say that in Haskell? Like, I want a number that is bigger than all other numbers. Is there a Haskell biggest int? Or like, yeah, big int for fold min. Yeah, m empty. There's also, I'm pretty sure there's actually a function that does this, right? Min folder min, yeah, but I swear there's a version of this that comes with the standard library. But anyway, okay, this is janky as anything, but it'll do. Let's try parsing our input. So main equals do. Input is read file input. I don't love this, but this is okay. Let's say crabs. Let's say let crabs equals crab. We're going to fmap over this, fmap over, oh, I guess crab of read, fmapped over. So rather than going from int to crab, this is going to go from string to crab, because we combine read from string to int and crab from int to crab. We fmap this over split on input. And then we just need to grab this split on function, which I think I had in day 4. 04 solve split. Why did I not do it? Cool, let's get winner, get loser, get winning number, words when, yeah. Cool. Sure, okay, let's do this. I used a slightly different version of this for days 5 and 6, I think. Words when equals this. Cool. So we've got a list of crabs, then we just say print solve crabs max crabs. Maybe we should bake this bit into the solve function, but this should be okay for now. Main. This is going to take a little second to think about it, but I think when we come in, this is going to be the correct answer. Perfect. Too easy. We smashed this, okay? The day 4 broke me. Day 7, easy. Crabs don't seem interested in my proposed solution. Crab submarine engines don't burn fuel at constant rate. Instead, each change of one step in horizontal position costs 1 more unit of fuel than the last. The first costs 1, the second costs 2, the third costs 3, and so on. Okay. This is not a huge change. Okay, this is okay, right? So each move costs more. So, okay. Let's quit out of this. Let's copy solve1 to solve2.hs. We'll go into solve2. So all we need to change is the fuel2 function, right? So where fuel2 before was this, we just actually need some extra layer on top of it, right? So before it was just this value. Now, instead of 3, it's... So where we had before... Let's draw this up nicely, right? So if we had a cost of 5 before, this is now going to map to 5 plus 4 plus 3 plus 2 plus 1, right? Because each step costs 1 more than the step before. So the first step costs 1, the second step costs 2, the third step costs 3. First step 1, 2, 3, yeah, okay. So n goes to, how do I say this? The sum, it's just the sum of I going to n, right? I equals 1. So this is all we do, right? So where before we just had x, we now take f of x, where f is this. So let's go where fn equals, f of n equals, well, let's say f of 0 equals, well, f of 1 equals 1, f of 0 equals, 0, f of n equals 1 plus f of n minus 1. That's what we want. And now if I solve, we start up with 37. Oh, because I grabbed solve 1, not solve 2. So now if I solve the test case, we end up with the same number. That's not right. This is definitely not correct. Am I grabbing the wrong? No, this n shouldn't be shadowed. 1 plus 5. Okay, let's go. What's this number? What's this called? What's this? 1 plus 2 plus... what do we call it? Let's just call it f. Screw it. Int to int. F of 0 equals 0. F of n equals 1 plus f of n minus 1. Oh yeah. You're right. I'm just giving back the number itself. Nice. Thank you. I was going to drive me a bit crazy. Now the answer should be 168, which is what we got. So now if I do main, we expect the answer to pop out pretty quickly. Hopefully my unit is big enough. Thank you very much, UberX. Huge help. I love to see it. It's great, right? You do the hard stuff well, and then you stumble at the last little like anthill on your way to the finish line. This is heating up my computer. We're spinning hard. The fan has kicked in. I wouldn't have. Yeah, I should have done the shorter. I'm gonna kill it and do the shorter summation because that's yeah. N times n plus 1 over 2. It's the classic. Is it Gauss? That classic like math story. His teacher set him busy work to add up the numbers from off. I hate this. Because I'm returning an int. The division by 2 is what do I want? Fractional. How do I let me just not return anything. It's still not going to work because I'm actually returning an int. What if I'm just like fast and loose with my types? Is that going to work? No, it still doesn't like it. Fractional int. To this day, I don't know the best way. I don't know what I'm actually returning here. Right shift. Well, but Haskell has like integer division, right? You can do 5 div 2. You can do 5 div 2. So there's like integer division, but I need fractions in case there's a remainder. Number fractional. I guess I just say like fractional a or float. There can't be a remainder? Oh yeah, there can't be. That's not what I wanted. Div 2. N times. Yeah, sweet. That checks out. And then this is just an int. Beautiful, thank you. Yeah, and yeah, that checks out. And this is gonna solve. Perfect. I owe that one to you. I would have gotten stuck there for a hot minute. Nice. But that was good. Day 4 took about 2 hours to fully crack, and this one took about 25 minutes. You've never seen Haskell? It's neat, isn't it? How tidy is this? Find me another programming language that solves this problem in 30 lines of code-ish. And this is with the test case included and stuff. You seem to have a mathematical mind, right? I recommend looking at it. Lines like this, super elegant.